Alright, as all these recordings are taking longer than I expect, I'm going to try to make this one perhaps a little more conservative. Let's try to do a quick review of the quantum Fourier transform, or really the discrete Fourier transform. Quick, discrete Fourier transform review. And then I'm going to talk about how if we can do the quantum Fourier transform, which I'll define, we can solve the hidden subgroup problem and thus do Simon's algorithm and discrete log and break factoring with all of those. And if time, I'll go over the quantum Fourier transform, but my guess is we're not going to have time, so let's get into this. So first thing I want to talk about the discrete Fourier transform, because the main and, there's really sort of two important parts to the standard algorithm for doing the hidden subgroup problem over abelian groups. It's doing a discrete Fourier transform over Z mod n, and then sampling from that and getting equations, Z mod n equations for the hidden subgroup you're looking for. So I'm assuming you've seen Fourier transforms, discrete Fourier transforms before, but I'll go over it quickly. The very basic idea is that you're taking a function, in this case a function from Z mod n to C, and you're breaking it down into waves, which are in fact actually eigenfunctions of the shifting map of Z mod n. And so we take omega to be some primitive nth root of unity. You can think of that as just being e to the 2 pi I over n. And we say chi j of x equals omega to the jx. And so really, you should think of chi j of x as being this function if we're going sort of 0 to big N, as being the wave, complex valued wave of frequency j across, this is length n. And the Fourier transform of f of x gives us these coefficients, ft j times chi j of x. So it basically gives you the amplitude, the complex amplitude corresponding to each frequency. And the way you compute it is, funnily enough, you'll notice that these formulas are very similar, because the inverse Fourier transform computationally and mathematically is basically the same operation as the Fourier transform. You just switch out omega with omega inverse. And there's a lot of, if you work with Fourier transforms before, whether discrete or continuous, you'll notice there's a lot of choices you can make, whether you have these 2 pi factors or you don't, or you have them outside or you have them in the inverse or the not. Nicely enough, because we're working in quantum mechanics land and we need our quantum Fourier transforms to be unitary, we are forced into making some actually unique choices, and these scaling factors keep the Fourier transform unitary. But there are still choices you can make, like you can choose any omega primitive root of unity and you'll get different Fourier transforms which work just as well as any other Fourier transform, or take any automorphism of Z mod n. There's a lot of choices you can make in a Fourier transform, and that's why sometimes it can be a little annoying translating between two things, because a lot of the choices don't matter. It just matters that you have such a choice. All right, so let's talk about the two discrete Fourier transforms that we'll need. Is that if we take the Fourier transform of f equals 0, so we're representing our function Z mod n to C, n will be like, oftentimes, we're going to have it be arbitrary, and you can represent arbitrary n states and do discrete Fourier transforms over them to solve these hidden subgroup problems, but typically we'll also work over n equals 2 to the n. This is actually, you'll use this for a large modulus n to solve factoring, for instance. And so the way we're representing our functions is the functions actually exist in the superposition of the state. So when we're doing our quantum Fourier transforms, we'll have some state, which will be, some underscore, bit strings. Let's say B is for bit strings. Let's put this in display mode because this is an important thing. B of bit strings of f of b, b. And this will be the superposition that corresponds to the function f. And so we're encoding our z mod n function, our function z mod n to c. The c values is given by the complex coefficients of this superposition. And so if I say f equals 0 like this is precisely the function that is 1 when the input b is 0, and it's 0 otherwise. So it's just one spike. And as you might know from taking Fourier transforms, if you have one spike, when you take the Fourier transform, you will get a sum of all of the wavelengths. Similarly, do I get minus? Oh, it doesn't matter for 0. It shifted a little. Similarly, if you shift the spike a little bit, you'll get sum of all the wavelengths, but convolved by this factor. And so the key Fourier transform thing we're going to need is that, say, H is a subgroup of a abelian group G, and our abelian group is Z mod n in this case, just to make things slightly simpler, but let me move this out. Then if f equals the sum over H, basically a function that's, you could think of as an indicator for HG, and I don't have the normalization factor here. I really should if I'm not being lazy, but imagine there's a factor here such that this has norm 1. And then if I take the Fourier transform, I will get this, which is exactly k over h perp. And you might be wondering what h perp is. Well, the nice thing about, really, this is the representation theory of G, is that we can talk about this group, G dual, which is equal to, do we have Hom? Okay, maybe not. Is the group homomorphisms from G to the units in C. It all falls in the circle. S1, actually. So, in fact, these are all unitary representations, too. And what we have is that we can represent every single morphism here also by a unique member of math BB z to the n. If our group G is G equals z to the n. And again, this depends on all our choices. This is not a canonical identification, if that's something you care about. That if we have, something from, we have to pick, and we pick the same root of unity, pick the same omega, pick same, omega n. And then if I have J in here, correspondingly, I will have the J homomorphism, which exactly sends an element G maps to J plus G. I'm mixing notation because I'm trying to do arbitrary group notation, but we're only working with abelian groups here, so maybe it's better to write H plus G here, so it's a little less confusing. If I will have a group homomorphism G that sends to omega underscore n to the power of J. Actually, that's not what we want. We want JG. That basically the element G sort of corresponds to omega n to the G, and we take its jth power. And this will furnish a group homomorphism from G to C star corresponding to J. And we say that an element K is in the annihilator of H if for all H in H, the corresponding K of H equals 0. And so what does that condition actually turn into? That condition turns into, if we're representing our Ks as, technically this is, Ks in H dual is a subgroup of the dual group, or in H perp is a subgroup of the dual group of G star, but we're representing them as elements in Z mod n via this morphism. that basically an element j in Z mod n corresponds to the morphism that sends g to omega n to the jg. So what would a k of h stand for here? Well, we know that every h in this group will correspond to some number. And so all it means is that we're looking for a j such that jh is equal to 0 mod n for all h and h. And if we further realize that, if we're in just the abelian group case, every subgroup h will be uni-generated. It'll have a smallish generator, which is really the period. Then we're just looking for j, which is a multiple of n over r, where r is the smallest period. And so when we take this Fourier transform and we get of some random coset of h, what we really get is we get, if we go back to our diagram, now we are in frequency space, our frequency diagram, we will get these evenly spaced bars, if we're just showing amplitude, that correspond to, again in the abelian case, to multiples of n over r. And all these bars will have phase given by this, which is the shift given by the randomness of the random coset. If it was the 0 coset, if it was actually h, it would just be 1. But we get this phase shift. But the nice thing, and I'm going to talk about the hidden subgroup problem algorithm, is that when we measure, all of these phases go away. And so then we just end up sampling random multiples of this. And so we'll get something of the form ln over r, where L is an integer. Now, zooming out, is there anything else I want to tell you about this? Yes, I've talked about this all in the case where we're working in a single cyclic group. The question you might want to ask is, well, shouldn't this work for all abelian groups? And it does. So what happens in this case? What does the Fourier transform and what does the corresponding all of this look like in this case? Well, all these not these formulas. All these formulas all work. I'll say these ones. So everything I said here will work for a general abelian group. And basically the Fourier transform, if I represent an element, let's even make this more general. Zn times Zn is the group for discrete log, so I thought maybe that's a good example. Well, if I look for, if I'm doing all of this, and I represent my elements basically like this, in superposition B, where A and B are in Zn and Zm respectively, then to do the Fourier transform, the quantum Fourier transform over Zn times Zm, you just do the quantum Fourier transform here, and then you do the quantum Fourier transform here. And that's everything. And you're good. And what will end up happening is you will go through this whole process, and I'll talk more about this soon when we do the hidden subgroup problem algorithm, is that you'll get these equations that will give you these ln over r's, but they'll give you two elements. We'll call it, E1 comma E2, such that if I take the modular, dot product of this with the subgroup, it'll annihilate it. And so this element will lie in the dual group, which factors as a product. So it's a product of the dual group. Everything happens in parallel. And you'll get this equation, E1 comma E2, that will lie in the perpendicular subgroup of H. But all of this feels like very, who cares? Why am I talking about all this? Why am I talking about the Fourier transform of a function that represents a random coset of H and G? Well, we're going to use that, and we're going to do that now to solve the hidden subgroup problem. in case, you've forgotten after 2 videos, I've been more technical these last videos, so I'm just going to review the hidden subgroup problem very quickly. You have f, some function, which you're given as a classical, poly-size circuit, and it's a function from G to some set S. You can represent its elements in bit strings. And it has a few properties. There's some subgroup H, subset of G, such that, first of all, f descends to a function like this, arrow to S. That just means that if I have an element of H, I'll have, because we're only doing the cyclic case, f of x plus h will equal f of x for every element of the subgroup H. And furthermore, and this is an important detail, this map will be injective. And so you can factor this into G to G mod H to S, and you'll get this injective map. And the question is, can we find H? And by find H, meaning find some generators of H. So that's our challenge. And now I'm just going to go over an algorithm to do it. I won't give it fully in terms of all of these gates and stuff, but we'll have this one subroutine, which I'll talk about the algorithm later for that subroutine, which, you can wave a wand, and if I give you a quantum state, it will give you the quantum Fourier transform over an abelian group of your choice of that state. So say you are working over some abelian group G that is, in the background, it's the product of these guys, Z n1 times Z n2 times etc., etc. And the first step is you want to prepare your a quantum state and uniform state over all the elements of your group G. Now, oftentimes there are easier ways to do this, but because we're just talking about the quantum Fourier transform, you can do this with the quantum Fourier transform because we know that if we start with the 0 state, so say we start with just 0, then we can apply QFT, and once we apply QFT, we will get this state. And I'll try to be more careful about keeping track of the normalization factors this time. Sum underscore G and G of G. And implicitly, we're going to have a lot of extra 0 bits. Some of these 0 bits we're going to start off with, we are going to compute on, and some of them I'm not even going to write down because they're going to be what's called ancilla bits, which we use to compute our classical functions, to do ands and ors and such things which are lossy in data, but making sure they're not lossy. So we also have a bunch of these 0 strings. So the first step we do is now we have quite a large superposition. These n's are often exponentially large in the size of our register. And so we have this superposition, and the next thing we do is we apply the function which takes this. It takes f, we can represent f as a classical circuit, f of G, and it takes, it adds it to the 0 to the n strings here. So basically the transformation, which one can do with classical circuits, so therefore you can do it on every single state in superposition, will get us from here, from this state, to now we've applied f, and we'll get this state. I'm going to copy this real quick, and we'll get this state, but instead now we have f of G. So now we're here, and now we're going to do something that when I talked earlier is technically an illegal move. We're going to measure some, but not all, of the quantum registers. This turns out to be equivalent mathematically. You can prove this just using conditional probability, that if I have some quantum computation and some of the registers aren't used in any of the quantum gates after a certain point, you can treat it like you measured just that register, and you took the probability that, you get one answer from that register. So I'll basically get some random f of g when I measure this register. But you can treat it like you also then get, and the probability you get this f of g corresponds to, again, you take the sum of squares of all the possibilities, and then you take the sum of the probabilities of all the possibilities that give you f of g, and you can choose, you can treat it such that everything else that you don't measure is still in some superposition. So what does this function what does this actually look like? Well, and what happens when we measure a random f of g? Well, something interesting is that we can decompose this sum into, I'll copy it again, why not? We can decompose it into a double sum. Yeah, I'll just do it down here. Where we do for sum g, we'll do g in instead g mod h. And let's do display mode so it looks less ugly. It gives me some time. Yes, okay. Sum g and g mod h of, again, f of g is constant. We don't know what h is, so we're just doing some algebra manipulation on this superposition that we've concocted. And then we can group all of these that we have now an inner sum, which I'll put in maybe left and then right. The sum underscore h in h of g plus h, or h plus g. And if we do this sort of represents our sum. We find all the unique f of g's. So what have we done? Well, we've partitioned our group into all of the cosets. And we've found these tags that sort of tag each of the cosets. And so when we measure this, what happens is we actually extract exactly one coset, interestingly enough. And so now we measure the second register, and we get a random f of g. And so we see f of g, but seeing f of g actually doesn't do much for us. We just see it. Cool. But what we're left with is very interesting, is we are left with now the sum underscore, keep track of the factors, 1, of the square root of absolute value of h. Put some dollar signs around this and have it not be happy with me because I'm not very good at LaTeX, it seems. Of sum underscore h in h of g plus h. And this is the state that we're left with after measuring. And this is a random coset. So now we have a random coset. Okay. Well, what can we do with a random coset? It's interesting. With a random coset, just to be maybe suggestive, again, think of it as we're in a cyclic group. Because all these examples are essentially cyclic groups, but like slightly more complicated. Even the products of cyclic groups. What does this superposition look like? Well, we have an element at G, and then say the period of H is R, and so we'll write like R is like this distance. Then we will get these spikes evenly spaced at R. And so what happens when we take the Fourier transform of this state again? If we take the Fourier transform of this state, well, we're going to get a lot of frequencies. We should expect to get frequencies that are multiples of R. In fact, just me laying down facts, and you can prove this by just sort of Fourier transforms preserve convolutions, and that Fourier transform of a coset gives exactly an even amount of these frequencies at these n over r's. This is not a difficult computation to do, and actually if you want to check your understanding of discrete Fourier transforms, I would suggest you do it. This is kind of the same fact as this fact, except descending to G mod H, but that might not be the best way to prove it, but it is about the same fact. So what you do now is you QFT again over G. Take the G QFT. And if we take the G QFT, now we get quite a different thing. We're working over H perp, which is the size of it is G over H. So we will get now I'm blanking out. Did I write down the constants over here to be nice to me, or did I not? Well, maybe I'll think about it for a second. So we take the quantum Fourier transform again, and we will get this state up to scale. Sum underscore, I think I wrote K in H perp, which again, the way this is represented is this will just be, if we're working with cyclic groups, multiples that annihilate R. So they'll be like n over R or ln over R for random L. And we get K and H perp of chi overline. Let's get the signs right, even though here it doesn't matter. G of H chi bar. Do we need this? It should be of K. Yeah. Of K. So we get this state. Cool. Now we just measure. So we measure this state. And when we measure this state, we're going to get a random one of these guys. A random one of these. And so we'll get a random thing that's like L n over R in the cyclic group case. And so in the cyclic group case, we'll get ln over R. If it's a product of cyclic groups, we will get something, if the product has 3 factors, we'll get something like A, B, C, such that if you dot this with your group H, you will get 0. And so by dotting it, how do I say this? It's like your group G is represented by all of these equations. And you'll have a subgroup H. If I multiply by A on this factor and B on the second factor and C on the third factor for any element of H, because you can represent it as a 3 tuple as well, and I take their sum, I'll get 0 in each of the factors. And so in all of these cases, the main design is like, okay, you've gone all the way down here and you've gotten some equation. In the case of a cyclic group, you get ln over R. In a case of a product of cyclic groups, you get ABC. How does this tell you the hidden subgroup, the original goal? How do we find the HSP? Well, for the cyclic case, you have ln over R. Okay. Well, you just do it a few times. And you get, L1, L2, L3, all times n over R. And you just do it a handful of times, and you take their greatest common divisor, and with constant probability, you will get n over R. And once you get n over R, and you can check the period once you know it, because you can just compute f, you just take n divided by n over R, and that gives you R, and this will be the generator of your hidden subgroup R. So you just do it a handful of times, and you take the greatest common divisor. In this case, in the general case, you'll get a bunch of these ABCs, and you can do a sort of generalized form of Smith normal form, where you're taking, it's kind of like doing Gaussian elimination and the Euclidean algorithm at the same time, but also with reasonable expectation, you shouldn't need a lot of equations to solve it. Like a common hidden subgroup problem that's not actually an application, but it's used in the pedagogy of quantum algorithms, is a problem called Simon's problem algorithm. And the question is like I have your group G is equal to Z mod 2 math BB Z mod 2 or Z2 to the n. And your hidden subgroup H is just generated by one element A. And so basically, and you have some function f, f from G, right arrow, S, whatever, doesn't really matter what the set is, just that you can compute it with some poly-size circuit. And you know that f is H periodic, so f of x plus a equals f of x. Okay, how do you find a then? Well, you do this whole algorithm, and in fact, the quantum Fourier transform over Z mod 2 is the Hadamard operation, and so if you just do the Hadamard operation on every single wire, that's the quantum Fourier transform. So we could even write out this whole circuit, like the whole thing. The circuit looks like, why not? We'll do it on 4 bits. We're going to say our Hadamards are this blue color. And so the first thing you do is Hadamard, 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 Hadamard on all of the 4s. And then this is sort of black box. We do the operation. If it's Z mod, let's say it's like Z mod 2 to the, okay, so there are more wires because we need more wires to compute F on another register. So say there's enough wires to compute F. Then we do a bunch of operations to compute F. So let's computing F right here. And then we measure, but again, actually we don't. Measuring is sort of like also a pedagogical tool. So we take a bunch of Hadamards again. So we don't have to measure, but it's sort of easier to think about it like you measured. But again, if I had done all this stuff and I hadn't measured at this point, the f of g would have just sort of come along. And then at the end, it'd be like I sampled an f of g and then I sampled a random element of the Fourier transform of the coset, which would be a multiple of the period of the coset. So you do Hadamards, compute f, Hadamards, and then you measure. And on the other side, what do you get? Well, you will get an element of math BB Z2 to the n. And what we will know about this is that the element we get, if I take its dot product with A, will be equal to 0. Well, if you notice, this is the field with 2 elements. And so if I just keep coming up with equations, eventually I can do literal Gaussian elimination, where Z mod 2 over a prime. And I do like n-1 samples, and with high probability, they're going to be independent, or with constant probability. Or maybe I need 2n samples. Who knows? Some constant amount times n samples. And I can do Gaussian elimination, and I will uniquely determine A. I won't even determine A like up to a scalar factor, because I'll just uniquely get A. So that's one example of how you can do it, where, and we have a full circuit diagram, assuming you have some way to do a circuit that applies F to 0 bits to solve Simon's problem. Now, at this point, we're 34 minutes in. And so I think I'll just talk a little bit about what happens in practice in quotes, because we're not really doing this as much, or because unfortunately, there's more unfortunate details. So what I presented here works for the discrete log problem, works for Simon's problem. It actually doesn't work for factoring. And the reason is because the equations you get are of this form, ln over r. And to know that, you need to know this n, or have an n large enough that's like a multiple of any possible period. Well, when you're doing the factoring RSA problem, what you're doing is you're looking for periods of random elements modulo n. So you're looking at these functions, like x to the I mod n. And you know the period will divide phi of n, which is the totient function of n, which is equal to p minus 1, q minus 1 if it's the RSA prime. And so you have to know phi of n to determine the period of this element, r. This is the function we're applying, and r is the element we're looking for. And so we do this whole process over z mod phi n. We get these equations, we figure out r, and then using r with high probability, we can use that to find some fun square decomposition modulo n, which with good probability will lead to something that has a common factor with n that's not n, and then we can factor. Okay. But the problem is, you need to know phi of n. But if you know phi of n, and you know n, you basically have factored n already. So to do this, you have to be able to factor n anyway. So it's a little different when you're doing... can you let me pause for a second? Hi, I'm back. I had to handle a quick noise issue. But yeah, now I'm going to talk about how things are slightly less nice when you're trying to solve the factoring problem, precisely because you don't know a multiple of this. So what do you do? What can you do? Well, you just do everything the same, but you do your Fourier transform like modulo some n, which is sufficiently bigger than like a multiple of r. It might have to be bigger than r squared. And so the way you would imagine this is like you're looking, because all this thing can do is it's very good at finding the periods which exist in this function f. So we know f has period r. And so in some sense, this is sort of like doing the hidden subgroup problem over the integers. And so we pick some modulus, some big modulus number m, and I think maybe it's fine if m is just bigger than r squared. And then we know that when we look at this function, you know, it might have a bunch of different values or whatever, but we know it will have a period of period r, mostly, because it won't. The problem with m not being a multiple of r, it almost certainly won't be a multiple of r, because we often choose m to be a power of 2, and so it's very unlikely that it'll be a multiple of r. Well, any m we choose in this range randomly. And so it will be periodic with this period r, all the way until we get like, we do this, and then suddenly it's not periodic because it cuts off. So we compute our function in superposition, all this, and basically this is like a representation of you could say this this top state here when we compute f of g with respect to g in superposition. And it's really close to being periodic. And so when we do all this, and then we take our discrete Fourier transform and we look at our frequency things, it's very close to being a clean frequency at the... Oh, well, this is a wrong diagram. Oops. No, these will be at r. I drew this diagram like there was a slight shift. There's no slight shift there. You know, the first thing will happen at r. So we'll get something that's a function that's very, very r periodic, but not quite. And so when we take the Fourier transform, we'll get something that looks like a bunch of spikes at n over r at, in quotes, in quotes, Lm over r, get these multiples of m over r, but there will be a little fuzz. So there will be a small chance maybe when you do a measurement that you'll get something off. But with high probability or with constant probability, again, a lot of these algorithms, especially them being randomized algorithms, you just iterate a few times, and with high enough probability, you'll get good outcomes. So there's little fuzz. All right. So what you actually get is also, it can't be at m over r. What you end up getting is the integer roundings with high probability. So you'll get this round of Lm over r. Okay. And then there's a bunch of math, and you can look up these continued fraction expansions, a bunch of elementary number theory that tells you how you can get samples of roundings of Lm over r, and you can turn this into being r with good probability. But I'm not going over that because I don't really think that's the point of, how the quantum's working to solve these hidden subgroup problems. The point is that with quantum fun, I guess you could say it, you can make a uniform superposition over all the elements. And then with the quantum fun, once you do that, you can apply F to basically have a quantum superposition that represents the graph of F. And then with this, you can sample, and you can quantum Fourier transform again, because you know that F is periodic, and this will give you random cosets, and those random cosets will have these H periods. And so, although the real story is ever so slightly different, there's a little fuzz on the signal, morally it's the same. And you don't have this problem for discrete log. You don't have to do any of this elementary number theory, whatever, blah, 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 for discrete log. The most you have to do is, calculate the probability that you get two things being co-prime in the discrete log case, modulo n. And so at this point, this is everything I want to talk about with the hidden subgroup problem and the discrete Fourier transform. For my last trick, and this will be the last video, finally doing the quantum Fourier transform. And to get a sneak peek on that, the quantum Fourier transform will basically be the f of t, but committed to a quantum circuit. And it's interesting how that can turn this m log m recurrence relation into a recurrence relation that's a standard like telescoping sum that gives you quadratic in log big N. But I'll talk about that in the next video.